Hey guys, so I'm going to show you how you would do a problem that looks like this if we're looking to see the limit as x is approaching -5 of x plus 5 over the absolute value of x plus 5. So the first thing I want you guys to know is that if you see an absolute value in a problem, absolute values usually indicate that you're going to be working with some type of piecewise function. And there's going to be a specific format that you're going to use for these absolute values in your piecewise function. So if we look at a normal piecewise function of the absolute value of x, when we have the absolute value of x, we know that if we're looking at this in terms of piecewise, we have positive x if x is greater than or equal to 0, and negative x if x is less than 0. So basically what this is saying is that if you're plugging an x value into this, if you're plugging a value into this that is greater than or equal to 0, it's positive. So if you're plugging in 3 is a positive value. If you're plugging in an x value that's less than 0, you're plugging in a negative value. So if you're plugging in -3, then you're working with a negative value because it's less than 0. And so we're going to use this piecewise function format in order to format our piecewise function for the absolute value of x plus 5. And even though we have x plus 5 over the absolute value of x plus 5, when we're working with the piecewise function format of this, we're only going to look at this x plus 5 that's inside of our absolute value. We're not going to worry about the function as a whole. We're not going to worry about the rational function, and we're not going to worry about the numerator right now. So right now we are just worried about the absolute value of x plus 5. And this is equal to, so for our original piecewise format with our absolute values, we have x if x is greater than or equal to 0. And then we have negative x if x is less than 0. But now let's use what's inside of our absolute value, since we have a little bit more information inside of our absolute value signs than we did for this equation here. So we have x plus 5, because that's what's inside of our absolute values, if x plus 5 is greater than or equal to 0. And so that means we're going to have negative x plus 5 if x plus 5 is less than 0. So this is the first form that I'm going to see for this absolute value, but we can work this out a little bit because we know that if we have x is greater than or equal to -5, because we can subtract 5 from both sides here. And then again, subtracting 5 from both sides here, we have x is less than -5. And so now rewriting this form, we're going to have that our absolute value of x plus 5 is equal to x plus 5 if x is greater than or equal to -5, and then we're going to have the negative values of x plus 5 if x is less than -5. So now that we reformatted this, we can go back to our problem and see what we're looking at as we're approaching -5 from the left and from the right, because if our limit is going to exist, so we're trying to find if our limit exists here. So if the limit as x is approaching -5 exists, what this means is that the limit as x is approaching -5 from the left is equal to the limit as x is approaching -5 from the right, because your limit as you're approaching from the left has to equal your limit as you're approaching from the right. And then one more quick thing is that when we're looking at these absolute values, if you were to have, say, the absolute value of x plus 5 minus 7 in the denominator, even though you have that -7 out here, when you're working with your absolute value in terms of the piecewise function, you only want to use what is in the absolute value signs. So you would ignore this -7. That's just a quick heads up, because sometimes you see stuff outside of those absolute value signs, but when you're working with these piecewise functions of absolute values, you're only working with what's inside the absolute value. For that piecewise function. And so the reason that this is important is because if we're only working with what's inside the absolute value, when we go back to the actual problem, we're going to have to plug in what we found for this piecewise function and then use it to determine the entire value of our limit. So drawing a little number line to kind of help us visualize this a little bit more. So we're trying to find the limit as x is approaching -5. So if we have -5 here, what we found is that if we are greater than or equal to -5, so that would be a closed circle. If we're greater than or equal to -5, we're going to use the equation x plus 5. But then if we are less than -5, we're going to have -x minus 5. And so now, I don't know why this is here. Oh, that's weird. I want to erase, whatever. And so now, looking at this, we have the limit as x is approaching -5 from the left, and then the limit as x is approaching -5 from the right. So when we're approaching -5 from the left, we have negative, in parentheses, x minus 5. So let's check out what we're working with here. So we have the limit as x is approaching -5 from the left. So in the numerator, we're going to have this x plus 5. And in the denominator, we're going to have negative x plus 5. Well, looking at this, I do know that, and I'm going to move this to the next page because for some reason this won't erase here. I don't know what this is. That's kind of weird. But we're going to move some of this over to the next page. Oops. Just to keep working with it because, oh, there we go, that erased, that's fine, okay. So we're working with the limit as x approaching 5 from the left, we have x plus 5 over negative x plus 5. So I know if I have x over x, this is equal to 1. If I have 5 over 5, this is equal to 1. If I have x cubed over x cubed, this is also equal to 1. If I have x plus 1 over x plus 1, this is equal to 1. If I have x plus 5 over negative x plus 5, this should be equal to -1. Because when you divide anything by itself, like this x plus 5 over this x plus 5, it should be equal to 1. But we are going to prove that this is true. So we have the limit as x is approaching -5 from the left. This is what we're working with. So if we're approaching -5 from the left, let's use some values that are very close to -5, but not quite -5. And remember, we're coming in from the left. So a value that's a little bit bigger than -5 could be like -5.1 is a value we could use. We could use -5.1. We can use -5.01. And then let's try an even closer number to -5, -5.00001. And so now plugging this into the equation, we're going to have the limit as x is approaching -5 from the left of -5.1 plus 5 over -5.1 plus 5. And so this is equal to, if we have -5.1 plus 5, we're going to have -0.1 over -0.1. So this is going to be equal to -1. And then if we do the same thing with 0.01, you're going to end up with -1. And then again, if we do the same exact thing with this -0.001, you're also going to end up with -1. So using a calculator, you can plug in these values into your function. And then we're going to do the same exact thing coming in from the right, because when we're coming in from the right, we have the limit as x is approaching -5 from the right of x plus 5 over x plus 5. This should just be equal to 1. So when we're coming in from the left, our y should be equal to -1. And when we're coming in from the right, our y should be equal to 1. But let's prove that this is true. So now we have the limit as x is approaching -5, from the right of negative, what's a number that's a little bit smaller than -5 from the right, but not too small? Well, we could have -4.9, -4.99, that dot's not supposed to be there, -4.999. So if I were to plug this into my formula, I would have -4.9 plus 5 over -4.9 plus 5. This would be equal to 0.1 over 0.1, which is equal to 1. If I were to have -4.99 plus 5 over -4.99 plus 5, this is equal to 0.01 over 0.01, which is equal to 1. And then this is also going to be 1. But there's one more value I do want to check to make sure that when we're coming in from the right, we are using this greater than or equal to -5, or making sure that this greater than or equal to doesn't switch to our negative value when we're coming in from the left. So for these values, we're going to check, as we're coming in from the left, we're going to check the value of -5. And then when we're coming in from the right, we're going to check the value of -5 to make sure that when we're coming in from the right, we're greater than or equal to -5, to make sure that's a valid equation that we're using. So when we're coming in from the right, if we plug in -5, we'd have -5 plus 5 over -5 plus 5. Well, in this form, we end up having 0 over 0, which is undefined. So actually, we are not going to have greater than or equal to -5 when we're coming in from the right. We're just going to have greater than -5. So this closed circle should actually be an open circle. And then we're going to take this out here. But now let's check to see if this is a valid equation when we're coming in from the left. When we're coming in from the left, we would have -5 plus 5 over -5 plus 5. This, again, becomes 0 over 0. So on this side, it's also undefined. So the one thing that we found now through this graph is that the limit, our f of -5 value, not the limit, but our f of -5 value is an undefined value. So we're going to have two open circles on our -5. So nothing is going to be equal to -5. We either have to be greater than or less than -5. But for these limits, your limit as x is approaching. So what we found with this is we found that our limit as x is approaching -5 from the left is equal to -1 of our f of x. And then our limit as x is approaching -5 from the right is equal to 1. Obviously, -1 is not equal to 1. These two are not equal to each other. Therefore, the limit as x is approaching -5 does not exist. So our limit for this problem should not exist, and that's because when we take the limit as x is approaching -5 from the left, it's different as we're approaching -5 from the right, and knowing that the rules of a limit for it to exist, they have to be equal to each other, therefore this does not satisfy that definition. Our limit does not exist, and then this is my favorite method to solve these types of problems.